My presentation will be on modeling and simulation. Some of you may not have heard that term before, so my perspective on modeling and simulation will be from a level where most anyone can understand it. I am not myself an expert in modeling and simulation, but I have been surrounded by people that are for the last couple of years and absorbing a lot of knowledge. And I want to share some of that with you, and particularly how does modeling and simulation play a role in advanced manufacturing. I am the director of the Riverstone Energy Center, which is a couple of miles down the street from here. And at the Energy Center, we have a few different programs that we manage. It's through the Halifax County Industrial Development Authority as our fiscal agent, and the Tobacco Commission is the entity that invested the time and the money into these programs that you see here today, including r&dcamee that's in this building actually. So there's been a lot of investments in our region to go after advanced manufacturing. I will share some of those with you today, but in particular we'll look at what we have at the Riverstone Energy Center, which is a modeling and simulation program, and how we may be able to leverage that to take advantage of some of these technologies you just heard about in terms of computer-aided design, computer-aided manufacturing, computer-aided engineering. What are the benefits of modeling and simulation in a manufacturing environment? The Council of Competitiveness in 2009 stated that it's a game changer. Modeling and simulation is a game changer for manufacturers. It is a technology that manufacturers will have to adopt or they will become antiquated and go out of business. I can tell the story of my grandfather. My grandfather was a tool and die machinist. He was one of the best in the industry. He worked on the first plastic coat hanger, the first Bic pen, the first vacuum cleaners, the switches that went into the Apollo spacecraft. He made all of the molds, plastic injection molds for those types of products. He did everything by hand. He had about 30 people working for him. And he drew all of the drawings that you saw in computer-aided design here today by hand on a big bench with an architectural drawing apparatus. Any change had to be made, crumble it up, throw it out, start all over. And he would get things down to the thousandth of an inch tolerance, all by hand and all in his mind. When technology, I remember going there as a little boy, and he would bring me around the shop and show me everything they're doing. And I started to see as I became older that there was new technologies coming out. And my grandfather was so old school that he would not change his ways. He would not adopt the CNC technology. It was computer numeric control. He still wanted to do everything by hand. Well, unfortunately, after 30 years in business, he steadily declined. His market went overseas to other groups that were using the new technologies, and he had to close his business after 30 years. I'm afraid that's what will happen to small and medium-sized manufacturers in the United States if they don't take advantage of the tools that I'm about to show you here today. Why is modeling and simulation an advantage? Well, first of all, it drives innovative product design. New types of production techniques can be solved with modeling and simulation. You can reduce the amount of prototypes that you need to do and the amount of testing that you need to do. You can predict what the performance of the product is going to be before you actually make it. Bottom line is you save money, you improve the amount of time that it takes to get to market, and you improve quality. These are all important components, especially considering that we're competing against a global market now, like my grandfather experienced. If you don't stay competitive with the most current technology and have the competitive advantage of these things I just listed, you will go out of business. To give you an example of how modeling and simulation is used, Boeing, 767, in the 1980s, they had to do 77 wind tunnel tests on different prototypes, physical prototypes that they actually had to build by hand. Imagine the amount of time and energy and cost that involved in the wind tunnel studies. 2005, because of modeling and simulation, they only had to do 11, and in the future, they want to get it down to 3. So, a 77 down to a 3. Okay, more than a factor of 20 reduction in the amount of prototypes that have to be built and the amount of testing that has to be done. GE uses it. Here's what they said, Bob Zacharias, that they can achieve more efficient, quieter, less emissions, they're competitively superior and bring these products to market faster by decreasing the design cycle time through less reliance on development testing. Caterpillar, they use virtual reality technology. We heard about some of them Caterpillar coming back to the United States, reshoring their manufacturing operations here. What used to take 6 to 9 months to do, they can do in less than 1 month now with modeling and simulation. And then Procter & Gamble uses this to predict catastrophic failure before it happens. This is the traditional model or workflow for a manufacturer. You start with an innovation. I'm going to take this out and move around here. You start with an innovation. Here, an idea. You design it in a computer. Then you build a physical prototype. You review that model. You make revisions based on your design review. You build a second prototype. You review that. Make more revisions. Another prototype. Review again. This can go on and on and on until you get to the final physical prototype that you want to manufacture and scale, and then you manufacture it. That's the traditional workflow. With modeling and simulation and virtual reality, what you can do in effect is start with an idea, design it, visualize it, all in one environment, virtually prototype the product in a virtual reality environment, make changes in real time to the virtual design, and come up with the final design before you go to a physical prototype. So this reduces the number of physical prototypes that you have to make, lowers the amount of cost, and it shortens your development time, and in the end you make a better product for the customer. These are the companies, Fortune 500 companies and entities that use modeling and simulation. I'll point out NASA because Leland was here on Monday and he spoke about the Curiosity mission to Mars. I was fortunate enough to talk to the mission designer for the guidance and control systems for the Curiosity mission that just landed. They use supercomputers in California and performed over 3 million simulations on that lander before it landed because they didn't have the ability or the luxury to even test one physical prototype in that environment. You get one shot. So instead of doing physical prototypes, what they did is they did all of design, engineering, modeling of the landing sequence in a supercomputer, performed that 3 million times over and over again until they got it right. And that's why when you saw a month or two ago when it landed, everything went perfectly. And these are companies you wouldn't normally think. Pringles Chips uses modeling and simulation. Their potato chips kept flying off the line, and they couldn't figure out why. They used modeling and simulation. They figured it out. They changed the shape of the potato chip, and now the potato chip doesn't fly off the line when they make them anymore. So when you say modeling and simulation, another term that comes out very often is high-performance computing, HPC. A lot of the models are getting more and more complex. They're getting more sophisticated, higher resolution, more accuracy, more variables being considered in the model. Therefore, you need to use not a laptop computer, but you need to use a cluster of computers working in parallel to solve a problem, which is what they call parallel computing. And in this day and age, it's called high-performance computing. All of the Fortune 500 companies, or Fortune 50, use this type of high-performance computing. They have the people, they have the computer systems or access to them through the national labs, and they have folks that work for them that know how to do this. But what about small and medium-sized companies? Do they have access to this type of computing? Are they going to be able to stay relevant and competitive with the big companies? Here's some statistics. This is called the missing middle. 300,000 manufacturers in the United States. 95% of them have fewer than 500 employees, so they're considered to be small and medium-sized companies. And these companies, these small companies, make up most of the jobs in the manufacturing sector. Most of these companies have no access to these computer simulation tools, none whatsoever. But by 2020, 98% of them are going to have to. That's only 8 years away. 98% of them, of all products, will be designed digitally. And most of our manufacturers today are not even using the technology yet. So that's why what you heard this morning with Siemens, David Keneally, what he's trying to do here is very, very important. For manufacturers, these small companies, medium-sized companies are going to stay relevant. They need to adopt this, and they need to do it quickly, or they're going to go out of business like my grandfather did. So what can they do, the small companies? Well, what's the problem? Why aren't they adopting these technologies? They're sort of stuck at the desktop. They're stuck at the laptop computer, and the laptop can only go so far. They don't have access to more tools. And most Tier 1 suppliers do not have access to the type of professionals, workers that have the knowledge and skills, and the software sometimes can be very expensive to get access to these type of computing capabilities. Here's the missing middle. If you look at the complexity on the bottom of the actual simulation you're trying to do, if it's a low complexity type of simulation, most traditional computer users have access, and there's a lot of users. The higher complexity modeling and simulation at the right side, there's only some of the very major Fortune 50 companies have the infrastructure, have the capital to do that type. But what about everybody in the middle? They don't have access to the technology. Here are some reasons that the Council on Competitiveness came up with why these companies don't have access to this technology. The software is not very user intuitive. The cost is too high for these small companies, and there's a shortage of expertise in this field. I was just at a modeling and simulation conference just east of here a couple weeks ago, and everyone talked about the same topic. We don't have people that know how to do this, and that's what we need. So for you students out there looking for a career path, where am I going to head? This is a very lucrative career. There's going to be a high demand. There is a high demand right now, and it's going to increase into the future for digital manufacturing, high-performance computing, information technology. All of those fields are going to be relevant as you move forward. So please consider that when you're thinking about your career options. What they came out with was, in the recommendations, that small businesses need to partner with government and universities to get access to this type of technology. What kind of things can you do with modeling and simulation in manufacturing? Well, you can predict how a product is going to perform. So modeling is a lot what you saw this morning. Modeling is building the three-dimensional model. What does it look and feel like? What is the geometry of the object? That is modeling. Simulation is actually taking that model, that three-dimensional geometry, and making it go through a various set of external circumstances like a force or a temperature or a vibration to see how it's going to perform. So there's a difference between modeling and simulation. So when you're trying to predict how a product is going to perform, such as how is it going to perform in vibration, stress and strain and failure, bending, torques, all of those types of forces that act on objects can be solved inside of a computer. You can understand how the product is going to perform on a thermal level. How does heat flow through the object? Is it going to be a heat sink, a heat generator? Do we need to add more surface area to that object to help dissipate away the heat? Is it getting too hot? And then in this, of course, the temperature that is generated inside that product will actually change the physical parameters. As the metal gets hotter, it gets more ductile, more able to deform. And so the models that we use have to be able to take temperature and stress and strain all together at the same time, which is called multi-physics, and there's software out there that will take into account the thermal, the stress, and the strain all together in one simulation. Composites are materials which are made up of various types of materials homogenized into one new material. Okay, that is a very sophisticated, hard problem to solve. There's not a lot of nonlinearities associated with a composite, so there's a lot of work to do in that field. We heard about composites being very relevant in terms of lowering the weight of aircraft and automobiles into the future. You're going to see more automobiles, more aircraft made with composite materials than you do today. Fluid flow prediction, which would be computational fluid dynamics. How does air flow around an object? How does fluid flow through an object? That can be done with CFD. You can also look at the process of manufacturing itself. When this part is being machined, when this part is being made on the factory floor, is there going to be a bottleneck? Is there going to be a part of the cycle where parts are going to begin to pile up because the other processes aren't keeping up? That can be simulated. So you can predict optimal plant layout and process flow using modeling and simulation. Another neat element of modeling and simulation is you can do workforce training inside a virtual reality environment where that equipment may be too sophisticated, too expensive, or too dangerous to work on, and you can't have a person working on the actual piece of equipment. You could train them inside a virtual reality environment. What are the tools that you need to do modeling simulation? You need high-performance computing. You need trained users. You need software. You need some kind of visualization technology. Those four components are the four major things you need. So let's go through each one. We'll go through software first. I talked a little bit about finite element analysis. This is where you break an object down into thousands or millions of little tiny cubes in the computer's memory, and you solve all of the equations that govern stress and strain or thermal distribution in an object across this mesh of little tiny elements, finite elements. It's called finite element analysis. Some of the off-the-shelf software that does finite element analysis, Siemens does do this. They talked about it a little. It's called FEMAP. Pro Engineer, which used to be called Pro-E, it's now called Creo Elements. They have finite element analysis built in. CATIA has it built in. Even Autodesk, AutoCAD products that Autodesk now own, they have a simulation package where you can do these type of thermal and finite element analysis right on the object that you're designing in that environment. There's other open source code that's free that you can use. And then there's computational fluid dynamic packages that you can use to do more fluid flow types of problems. So that answers the software side of the equation. It is accessible. The software, for example, go back, Autodesk is very affordable. In fact, if you're a student, you can go down to the website and download it for free and start playing around with it and starting to learn how to. It's a very good entry-level system for students to play around in to get an idea of how computer-aided design, how modeling and simulation work. So any students out here that want to play around with it, you can download Autodesk for free. High-performance computing. This is supercomputing, right? I'll talk a little bit later about how we have a supercomputer now in our region. It's by Noblesse. It's a Cray supercomputer. But these tools are very expensive to use. And so traditionally, only big companies or national labs or major universities had access to supercomputers. But now things are changing, and every day you and me can access a supercomputer, and I'll show you how to do that. Everyone's heard of the cloud. When I first heard about the cloud, it was very abstract to me. I didn't understand it. I didn't like it. I don't want all my files somewhere else. I don't know how you all feel about that, but I like having my files on my computer. I don't want somebody else having control over them, being able to see them if it's confidential information. So I was very skeptical of the cloud when I first heard about it. But now I'm starting to like the cloud. And the reason is because it's bringing high performance computing to the average person on the street. Here's an example of that. At Purdue University, they have a supercomputer, and they wanted to make it available to small and medium-sized companies and people like you and me. And so what they did is they formed a consortium called Hub Zero, which has all of the cloud-based technology on the high-performance computing systems. And they did this and built tools, open-source tools that anyone can use to simulate nanotechnology. That was their first project. It was called NanoHub. And so 27,000 users now across the United States can go here, and for free, they can use a supercomputer and use the tools that are already there through a web interface and simulate something to do with nanotechnology. They said, we want to repeat this with manufacturing, and so now they're starting an initiative called Manufacturing Hub. .org, and they don't have a lot of tools in there right now because it's just getting started. It's sort of like the App Store on your iPhone. So they have all these apps that users build and put into the store, and there's only one in there right now. But NanoHub, when they put out this model, it started with one, and then it got to dozens and then hundreds of different models that you can run your program on. So now with Manufacturing Hub, they have one application in there now, and they're going to continue to build on that, and users like you and me can go in there and for free access this, do some type of simulation for a manufacturing process, and get the result using their supercomputer. Yep. Here's all the users on NanoHub across the United States. They're going to do this with the manufacturing side of it, and I think it's going to be successful. Let's go back here. Another cloud-based high-performance computing supercomputing system is called the Extreme Factory. They already have 18 applications. Some are free on their supercomputer. They can do virtual prototyping, computational fluid dynamics, on that website right there. So whoever wants this presentation when I'm done, just email me. I'll send you a link to it, and you can get all of these resources. Another one I found, SGI Cloud, High Performance Computing. There's their website. And Amazon. Amazon has a supercomputing cloud-based solution now called Amazon EC2 Cluster Instance. Low cost. You can run any jobs anytime, anywhere around the world, and it's pay as you go. So very cheap. Imagine if you had to go buy a supercomputer. Imagine if you had to hire the IT professionals to run and operate that supercomputer. It would be in the millions. But here you can access it when you need it. They already invested time and money into it. Again, I'll mention Nobliss. This is in Danville. I think this is a game changer for our region. We have a Center for High Performance Computing in Danville now, and what made this possible is the Mid-Atlantic Broadband Cooperative. MBC, which is at Riverstone, their headquarters, runs all of the fiber cable throughout Southern Virginia, connects all the industrial parks and educational institutions with some of the world's fastest highest bandwidth fiber connectivity. So what this means is we can transport large amounts of data in a shorter period of time, which is why you see data centers moving here to our region now, like HP and Microsoft's cloud is coming here to our region, and why the supercomputer located. And there was just a project announced where they're going to use it for genomic sequencing now. So you're starting to see projects come. I think this is a game changer for our region, and we can leverage this technology for digital manufacturing. So I talked about how now we have access to HPC. The visualization part is what I'll talk about now. Most people are used to an LCD flat panel screen, is what you normally use when you're doing some type of design on a computer. But now you can use something like this, which is virtual reality technology, which is at the Riverstone Energy Center. And if you come to the tour today at 3:30, like David said, you will get to see the Modeling and Simulation Center as well as the other things we have there. And what this is almost like a hologram. If you've ever seen Star Trek, the holodeck that's on Star Trek, that's what it feels like. It feels like you're in this virtual reality environment, fully immersed inside of it. Truly impressive. You can really get inside your design, whatever it be, on a molecular level, all the way out to a Google Earth, and you're flying into Paris. So it doesn't matter what scale you're looking at, you can do it inside of this cave. Again, you can use it to do a design review. You design something, you look at it inside the cave in real life-like scale, and you can really see things that you wouldn't see before on a two-dimensional screen, and you can make changes and see the change inside the cave while you're in there. You're going to see new types of relationships you weren't able to see before. And you can do computational fluid dynamics, like how air is going to flow around a vehicle or an aerospace structure there. So that's the visualization piece. I think that's important. How you look at the data is key. Then trained users. This is the part I told you about. There's not enough workers with the skills to be able to do this. This is all new. A lot of this is all new. And so these are new classes that have to be offered to students how to do this. Old Dominion has a program in modeling and simulation that you can tap into. ECPI has a modeling program. Associate and bachelor's, am I correct in saying that? Intel, I met with the director of modeling and simulation at Intel, and they have a program where they need people so badly in modeling and simulation that they're willing to invest their software, their equipment, their technology into an educational institution for free if you will provide the teachers to train the students. So they're piloting this around the country now, but that's how desperate they are to get people that know how to do this type of thing. So I'm going to look at some of the cutting edge technologies. So glad Dr. Chris Williams from Virginia Tech is here to talk about additive manufacturing. But I think this is going to be a new arena for modeling and simulation. Additive manufacturing is where you can build up a new product by printing it layer by layer. What this means is instead of cutting away material, which is subtractive manufacturing, you can build exactly what you want layer by layer. There is no material subtraction. You're just adding material where you want it. You make the final product that way. What this means is you can make any complex internal mesh structure that you want to make that product lighter. So think about the infinite number of geometries that you can come up with to potentially fill space with a solid or an open solid and make the product lighter but still have the stress and strength characteristics that you want. You make the product lighter with the same strength using additive manufacturing. But imagine trying to solve what the strength of that material is going to be using some type of model. Remember I showed you finite element analysis where you have to break the part down to little cubes? Well, if it's a solid material, it's easy to break it down to little cubes. If you're doing something with a complex internal structure like that, you have to make those little cubes very small to mimic that part. And so as you make them smaller, that means you have more cubes now you have to solve for in your computer. So what this means is you're going to have to use high performance computing to solve the stress and the temperature distribution on these types of products. So I think additive actually changes modeling and offers a new opportunity for modeling. Some of the things we're doing at Riverstone, we have some intern students that are working now through Longwood University's DigiSpired program that we're trying to integrate the Kinect technology from Microsoft into the virtual reality cave I showed you. We're not there yet, but we're making some good progress. Basically, Kinect is a way that you can measure, you heard about the scanning, the 3D scanning using lasers. Well, this Kinect system that you can buy for $200 and attach it to your game at home, this little device was designed and built in Israel. Microsoft bought this company app. Phenomenal technology. Every 30 times a second, this device can scan the inside of a cube in your room, wherever you're at, and form a 3D point cloud of everything inside that room. It does that 30 times a second, and then feeds that information to the game. So what it does, essentially, is it tracks your body. Remember Wii, the Wii game, you use a little handheld controller, it can track where that is. It couldn't track your body. Well, Microsoft changed the game when they came out with Kinect, which is tracking your skeleton. So imagine now we're in a virtual reality environment. We're surrounded by this environment. We want to move. We want to manipulate it. We want to interact with it. So that's what we're trying to do with this technology now. Is take this off-the-shelf technology, use a software development kit that comes with it to actually manipulate the objects within the environment. This gives us more freedom to design, more freedom to do workforce training and those types of things inside that cave. Here's some organizations. Again, if you want to learn more about digital manufacturing, high-performance computing, these are organizations, websites you can go to, and you can get plugged in. You can become a member of the organization, get their emails, go look at the resources they have on the internet, start learning about it. And one final thing I'll say is modeling is the first step in manufacturing, the design process, the engineering process. Prototyping is and manufacturing is what they can do here at the R&D Center for Advanced Manufacturing. They also do design and engineering. And then the final coding, which is now at the National Center for Coatings at Riverstone, is the final step in the manufacturing process. We have all the tools, including the high-performance computing and the bandwidth and the fiber in our region now to do this whole process. So I think we're a very competitive and attractive area to do business for manufacturing. So that I'll end and take any questions.